Welcome to day 3 here in Algebra 2 class of our Algebra 1 review. Call it our Chapter 0 to kind of start the year off here on a good foot. Um, and today's all about absolute values. So we looked at the past couple days function notation and how to graph a line, how to turn information into the equation of a line. And now we're going to look at a function that, although it isn't linear, its graphs have linear components to it. And you've probably seen some of this before. You're familiar with this, hopefully. But an absolute value of a number is its distance from 0 on a number line. And it's shown with these straight brackets here. And we know that an absolute value must be positive, and then because it's a distance measurement or 0. And then we also know that because it cannot be negative, the graphs of absolute values tend to make a V shape. So it's, if you imagine like a laser beam hitting a mirror and bouncing off, that's kind of what the graph looks like. It's just trying to avoid the negatives, so it kind of reflects and bounces back the other way. But the sides of that V-shaped graph are both linear. So we tie it in as we get ready to begin our chapter 1 with linear functions. It's a nice addition to this chapter. All right, I've included a little reference for you here at the start. The first thing we're going to do is look at absolute value functions and solving them when they're in equations that contain an absolute value. So you can see properties of absolute values are listed below. They kind of act like a quantity, like a set of parentheses. So there's a multiplication component to them. You can see the output of an absolute value must be greater than or equal to 0, provided that that input is, in fact, a number and not an expression. That's number 1. Number 2 says that the absolute value of a negative number is going to be the same thing as the absolute value of that positive number. And then number 3, again, since it's kind of acting like multiplication, if we have a product inside an absolute value, we can simply multiply the two absolute values of those components together. And same thing with division for number 4 there. So just some properties that we've covered before. Again, this is a reference section. This isn't something to memorize or anything. It's just something to look back to as you go through your work. The main thing we want to focus on when we're concerning ourselves with solving absolute value equations is if we have an absolute value that's set equal to a number. Remember that absolute value has to make something that's 0 or greater. Provided that that's the case, what we do is we split it up. We say the stuff that was inside the absolute value could be making a positive number, or the stuff that's inside the absolute value, notice I didn't change anything about it, it could be the negative version of that number that it was equal to up above. We don't really know if that ax plus b is making a positive or negative result because the absolute values would kind of take away that negative sign. So we have to solve both of those. Typically when solving absolute value equations, we get 2 answers. The second part there, if we have this equation and the c value at the end is negative, we know instantly that it is a no solution situation because an absolute value cannot equal a negative number. So that's kind of helpful. We can very quickly answer those questions. All right, so example 1, solve each equation. You can see these problems already have an absolute value isolated. So for letter A, the absolute value of some number minus 4 is 6. Well, quick check, yep, an absolute value making a positive, that's good. So we can go ahead and set up our 2 scenarios here. That x minus 4 that's inside, it could be making a positive 6. Or that x minus 4 inside could be making a negative 6, and the absolute values take away the negative. We don't know. So we got to solve both cases. Either one would make that equation true. Real simple algebra steps once we get those little equations set up. I call them mini equations. X equals 10, and same algebra step over here. Okay. Before we move on, just notice that right here I left that as x minus 4. I did not take that negative sign and change it to a positive or anything like that. When we were setting up the left side of those little mini equations, they are the exact same as what was inside the absolute value up above. All right, letter B, let's check and make sure that this is possible. We've got an absolute value that equals negative 5. Ooh, an absolute value cannot produce a negative output. By definition of absolute value, it has to produce a positive or zero output, so this is instantly a no solutions case. Nice and quick. All right, next we start adding in some more algebra steps. You can see that now our equations look a little bit more complicated. That's because the absolute value has not been isolated. So we cannot make that call whether or not we split it up or say no solutions just yet. What we have to do is get the absolute value isolated. So I want to isolate this. I need to subtract 5 from both sides as my first step. All right, now I can treat this like a problem from the last slide. Absolute value equals a positive. That's good. I can set up my two situations and solve those independently. And I get my two solutions. When you have more than one solution, sometimes I'm not picky, particularly about leaving the answers written this way. Sometimes you will see it written, though, if you're checking your work in the back of the book or looking at an answer key or something like that to check your work. Sometimes you'll see more than one solution listed in a set with those squiggly braces like that. It means the same thing. All right, problem number 5. Here, to isolate the absolute value, I'm going to divide both sides by 4 first. I cannot make the call whether or not it's no solutions until I divide that 4 out. All right, so 2x plus 7, that absolute value equals positive 4. Okay, that's good. We can split that up into our two cases. Stuff inside could be positive 4, stuff inside could be negative 4. Here the steps are to subtract 7 from both sides and then divide by 2. I'm going to go ahead and use that set notation. Let's subtract 7. Excuse me. And for this one, the solutions we arrive at are negative 3 halves and negative 11 halves. If I wanted to check my work, all I would have to do is substitute those answers back into the original equation and make sure it made a true statement. Problem number 6 is really tempting to look at this negative 11 over here and say, ooh, it's no solutions. But what we first need to do is isolate the absolute value. We cannot make that decision yet whether or not there's no solution. So let's add 3 to both sides. Negative 2 times the absolute value of 5x minus 1 is negative 8. I have to divide away that negative 2 to isolate the absolute value, and now look at what we got. 5x minus 1, that absolute value equals positive 4. This one is totally possible. So we'll set up our two cases. 5x minus 1 equals positive 4, or 5x minus 1 equals negative 4. We'll add 1 to both sides and divide by 5. So x equals 1 is one of those solutions. Let's do our other mini equation, 5x equals negative 3 after I add 1 to both sides and divide both sides by 5, get x equals negative 3/5. Again, not too terrible, as long as we remember when we can make the decision, whether we split it up and do two equations or whether we just say there's no solutions. Be very wary that you have the absolute value isolated before you make that call. All right, now we move on to graphing absolute value functions. And here you can see a picture of what an absolute value graph looks like. That's just a very basic y equals absolute value of x. You can see it's a very linear graph, and then it just kind of reflects to make a mirror image. They're very symmetrical graphs, and it just kind of avoids being a negative output. And that makes sense with what we saw our absolute value properties telling us. The steps to graph, I break it down into 3 simple steps. We're going to make a table of values, which is probably how you first learned how to graph anything. Step one is to figure out what would zero out the inside of the absolute value. I call that the most interesting value of x, or MyVox for short. And what that's going to tell us is that's going to tell us the x value of that vertex point, that point in the graph where it reflects. Then we're going to build a table of values around that x value. Usually we want to have maybe 5 values in our table of values with that MyVox, that most interesting value of x in the middle. And then we're just going to plot the points and construct that graph. So pretty straightforward steps as long as we can correctly find that vertex x value. Let's give this a go. All right, so for problem number 1, let's make our table of values. I'm just going to start that process by making a basic T-chart, nothing fancy here. And then I need to figure out what zeroes out that interior. Well, the inside of the absolute value is just x plus 3. I'm ignoring everything else for now, just what's inside. Where would that equal 0? And if I solve that little equation, you can probably do most of this in your head, actually. I find that x equals negative 3 is that value. So if I plug in a negative 3, it will zero out the absolute value, and then I'll have minus 2 as an output. I know that negative 3, negative 2 is the vertex of that absolute value graph. And then from there, I'm going to fill in my table with 2 values on either side. And we remember the symmetry of the graph. We should be able to use some reflections to help us out here. But we just plug them in and find the outputs that go with them, and we should see an image show up that looks like that V-shaped graph we saw earlier. So if I plug in a negative 5, I will have negative 5 plus 3 inside the absolute value. That's negative 2, which has an absolute value of positive 2. Then I apply this negative sign out front, so I'm back to negative 2 minus 2 is negative 4. So negative 5, negative 4. Let's try that same routine with a negative 4. And I'm just kind of talking through this. You could be doing scratch work off to the side if that helps keep your thoughts organized. It doesn't take much time to plot these out. So negative 4 plus 3 is negative 1, absolute value of which is positive 1. Then I throw that negative on it. Negative 1 minus 2, negative 3. And as I'm plotting these points, I'm pretty happy about the fact that I see a straight line of points leading up to that vertex. I should see a mirror image start to show up afterwards. So I'm expecting this graph to come up to the vertex and then head right down afterwards. So let's see if we have that happen. If I plug in a negative 2, negative 2 plus 3 is 1, absolute value of which is still 1. Add the negative onto it, negative 1 minus 2, negative 3. There's that mirror image starting to happen. Negative 1 plus 3 is positive 2, absolute value of which is positive 2. Tack on the negative on the front, negative 2 minus 2, negative 4. And then we can see that straight line graph continuing off to the right. So there's our V-shaped graph. This one is a V-shaped graph where it opens downward, and that can happen. Just notice the 2 linear components making it. That's it, just 5 simple points in our table of values, and we are set. All right, next one. Let's make our table of values. What value of x would zero out just the inside of this absolute value if x was 1? Then I would have 3 times 1 minus 3. That would produce a 0 output. If I plug that 1 into the entire equation, the absolute value zeroes out, and then I subtract 2 in the end. My vertex should be the point 1, negative 2. And let's fill in the rest of our table of values around that. Okay, if I plug in a 0, then I would have absolute value of negative 3, which is 3 minus 2. That's 1. So 0, 1. And let's plug in this 2 next, just to see if we have that symmetry showing up in our y column. If I plug in a 2, I get 6 minus 3, 3 inside the absolute value. 3 minus 2 is positive 1. So sure enough, I'm seeing that symmetry start to show up. Hopefully, we'll see that pattern continue and the graph doesn't bend off any weird way. It has those nice straight sides to it. Negative 3 minus 3 is negative 6. Absolute value is positive 6 minus 2. 4. And if I plug in a 3, 3 times 3, 9, minus 3, 6, absolute value is 6, minus 2, also 4. So negative 1, 4, and 3, 4 are the next points on that graph. And look at those nice straight sides on that absolute value graph. Number 7, more of the same, right? We're just adding in different numbers in different places to see how we might change. This is more practice in going through our order of operations to determine that Y column. And yes, there is a way to have the calculator do this for you, and it's wonderful. But this practice early on in the year of working through the mental math can be a really, really big help. So I encourage you to do that. I know that the value of 4 will make the absolute value zero out. And then my output will be a negative 3. I'm going to spare you a little bit of my jabbering as I work through the mental math. Okay, so if I fill in my table of values around that, let's see what happens. If I plug in a 3, I get negative 5. If I plug in a 5, I also get negative 5. If I plug in a 2, I get negative 7. If I plug in a 6, I also get negative 7. And that's off our graph just a little bit. I'm just going to kind of approximate where those points would be, just to make sure I'm seeing those straight line, those points line up to make the sides of that graph. All right, this is a good opportunity to talk about the domain and range of a function. The domain are all x values that we can successfully input into a function. And for all absolute value equations, the domain is going to be all real numbers. And you can write all reals. You can use the symbol that represents the real numbers, which is like a double bar R. Or you could say this, which it looks like an ordered pair, but it means every number from negative infinity to positive infinity. I'm okay, I guess, if you abbreviate it ARN for all real numbers. Any of those are fine. I'd probably recommend either all reals or the real numbers symbol for now. The range, instead of x values, those are y values. What heights do I see this graph output? So I'm just going to measure this graph against the y-axis, and I can see that at a height of negative 3, that's where I start to see the graph, and I see at every y value underneath that. So my range is all y values that are less than or equal to negative 3. And again, that's just describing the graph as far as where it shows up. And it's describing the function as far as what types of inputs are allowed and what types of outputs are we going to see. We can input anything. We're always going to get something out that's less than or equal to negative 3. It's a good descriptor. And then finally, I do apologize. This should say y equals. It says graph each equation, and I don't have an equation written there. But what happens when there's more than one absolute value? What we get is a really neat looking graph. It's kind of like segmented and joined together in a weird way. But what we're going to do is we're going to look at 2 vertex points because there are 2 absolute values here. From this first absolute value, if I had an x value that was negative 1, that would zero out the first absolute value. Here, I'm going to start to try and color coordinate this one a little bit. And for the second absolute value, if x were to equal negative 3, that would zero out that second absolute value. So I just want to make sure that my table of values includes both a negative 3 and a negative 1. And then I want to fill in with numbers around those. I should be able to see the straight line segments that are connecting this. So I'm going to toss in a negative 4, a negative 2, and a 0. All right, so let's start by plugging in our vertex points. If I plug in a negative 3, let's think about this. Negative 3 times negative 2 is 6, minus 2 is 4. So I know that first absolute value is outputting a 4. minus sign in the middle, if I plug in a -3 in that second one, it zeroes out. I know that output height is 4 when x is -3. Got that? Let's try our other vertex, -1. If I plug in a -1, it zeroes out the first absolute value, minus plugging in a -1 here creates a 2. So I know -1, -2 is another vertex point, another point in the graph where I see some type of break in the line. The line changes its slope there. Okay, and let's fill in the gaps. If I plug in a 0, I would have 2 from my first absolute value minus 3. So 0, -1. If I plug in a -2, then I would have 2 minus 1. 1, so -2, 1. And look at how that makes this line up perfectly. Isn't that nice? From the blue vertex moving onward, you can see it's kind of charting a path like this, a linear path. We could add more points if we wanted to be more confident in that. But for the sake of time here in this video, I'll leave that as is. If I plug in a -4, I get 6 minus 1. 5. So the point -4, 5, and then that's going to chart off this line segment the rest of the way. So you can see we get kind of a neat little bendy graph. Well, not bendy, that's not a good word. But it makes a couple of turns instead of just one. It's not just one V-shaped graph. Moral of the story here, we're practicing with something that is sort of linear, and we are looking at handling order of operations with absolute values. Are you likely to see very many of these show up in your math career? Probably not, but it's just a really cool extension of what we've been covering in class the past few days. So hope you've enjoyed this little review section. I hope you feel more confident as we get ready to head into our content here in Algebra 2. And yeah, let's get this started the right way.